So, welcome to our next lecture in the Internet Seminar. And the third chapter is about the form method for elliptic operators. So, we want to apply the method of defining operators by forms that we introduced in chapter 2 to a specific class, rather large class of differential operators of second order, which are elliptic operators. The model case of such an operator, the most important example will be the Laplace operator, but we will have some more general thing. And in order to get there, we need some we have to find a good Hilbert space where we can define the forms and then prove that everything goes right in the sense of the last chapter. The natural choice for a Hilbert space for functions is L2, so square integrable functions. And then it turns out that the classical derivative is not the right thing. It doesn't fit well to the notion of an L2 function. The classical derivative is a thing of at every point there is a limit stuff, and L2 is almost everywhere. This doesn't fit well. And we have to reconcile this. And this is what we will do in the beginning of this lecture. And for this we need some basics from integration theory about modifiers, about convolution, that we hope are things you know. For the students here, I'm rather sure you know, because this is part of the integration theory course. And to be sure that everyone is on the same page, in the lecture notes there's a section 1 where all these things are recalled, which I will skip now, so I'll go directly to the section 2, which is about reconciling the notion of derivatives or of differentiability with L2, and this leads to so-called weak derivatives. So what we will do is we will weaken our notion of differentiability. And just to give a small motivation, what happens if you start with a function that is derivative in the classical sense? I forgot that. So for all of this lecture, as a standing notation, omega is just an open subset of the n-dimensional real space, an open subset of our Rn. And let's start with a differentiable function, so k times differentiable, and take some multi-index that is of length less than k, so you can take the alpha derivative of u. And then there is a formula of partial integration somehow. So if you take a nice function, and let's take a really nice function, so arbitrarily often differentiable with a compact support in omega, and then you have the following formula for partial integration. So if you multiply u with the alpha derivative of phi and integrate over omega, you can start to do partial derivatives, and whenever you flip one derivative from phi to u, you get a minus sign, and usually you get some boundary integrals. But as our function phi has a compact support in omega, so there is a neighborhood of the boundary of omega which is 0, so all the derivatives are 0 there, so all the boundary integrals vanish. So what we only get is a bunch of minus signs, and then the integral the other way around, so alpha derivative of u multiplied with the phi. So this works for every ck function and for every so-called test function cc infinity. In CC infinity. And it's worthwhile to note that this is in some sense unique. So this function d alpha u, that fulfilling this equation is unique with this property, at least in a really large space. So at least in the space of all locally integrable functions on omega. L1 log, the locally integrable functions. So integrable on every compact subset of omega. And well, we will see in a moment that d alpha u fulfills this equation, and at least in L1 log you will not find another function that does this. And why that? That follows from the following important lemma that we will use several times in the sequel, and that's the so-called fundamental theorem of calculus of variations. So, fundamental theorem of calculus of variations. And this tells you, if you have such a locally integrable function, and you know that the integral, and for all test functions, so for all compactly supported, arbitrarily often differentiable functions in omega, you know that the integral over omega of v times phi is 0, then this implies that v is 0. And obviously you have the other direction, so if v is 0, all these integrals are 0. That's the boring direction. The interesting one is going from right to left. Whenever you know that all these integrals vanish, then v has to vanish almost everywhere. It's an L1 log function. Okay, and once you have that, you see that there can only be one function in L1 log doing this. Okay, so let's prove this. Yeah, as I said, there is an easy direction and an interesting direction, so this one is clear. Let's go from right to left. And then we have to treat some technicalities. If the domain, this omega is unbounded or has a bad boundary, we have to care for this. So we have some auxiliary domains, omega j, or close to the boundary we could have problems. So we do the following: we take all x in omega that have a modulus less than j, so are inside a ball radius j around the origin, and whose distance to the boundary of omega is greater or equal than 1 over j. So we stay away from the boundary and we cut everything that is too far away from the origin. Nevertheless, this omega j is a partition. No, it's not a partition, but it covers our omega. So this is a growing thing. So if you take the closure of omega j, you are always contained in omega j plus 1, and all these omega j's are contained in omega. And if you take the union of all these sets omega j, you get all omega. Just because every point is in some ball around the origin and has some distance to the boundary. It's an open set. Okay, so, and now the aim of the proof is to show that v is 0 on omega j for all j. Once you have that, so v is 0 almost everywhere on omega j for all j, and once you have that, you take the union of the null sets corresponding to omega j, and you get v is 0 almost everywhere on omega. Okay. And then what we consider is the following function. You take your function v and you cut everything away that is not in omega j plus 1. One remark at this point. Later on, I will, with a slight abuse of notation, regard this function Vj somehow as defined on the whole space Rn. On the whole space Rn outside of omega V is not defined, but somehow it's an understanding that 0 times undefined is 0. Or you can also say I take an extension by 0 or something. But we will have this several times during this lecture. So whenever there is a characteristic function times something undefined and the characteristic function is 0, then this has to be understood as extension by 0. Okay, so but what we do is we just cut away everything of V that might be too far out or too close to the boundary. And then let's show that this function Vj is 0. The first thing to note is omega j plus 1 is contained in a bounded set, so its closure is compact. So this function, as V is L1 log, this function is in L1, and as I said, I will see this as a function at L1 of Rn. Okay. Now take some function theta, so we will construct a pseudo modifier to flatten out things. So take some function theta that is a test function on the whole space with a support contained in the unit ball, so B01, the ball around 0 with radius 1, the unit ball, and normalized in such a way that if you integrate all theta around all of Rn, you get 1. So a usual starting point for a modifier. If you do not know about modifiers, go back to section 1 of the lecture. The toolkit for modifiers is in there. So, now, the aim will be to now take the modifier theta t and then take t small and convolute Vj with theta. So, and this is also the reason if you wondered why I take j plus 1 here, because now I will work on the smaller set omega j. So if you take an y in omega j, I need some security distance. Because if I modify, I always flatten out things a little bit and increase support, so I need some security distance here. So for y in omega j and t less than what I will call epsilon j, which is the distance of the closure of omega j to the complement of omega j plus 1. So we have these increasing sets omega j, and they all have strictly positive distances, and I take a t that is less than the distance between omega j and anything that is not in omega j plus 1. And now, as we want to convolute, take the function phi x, which is theta t of y minus x. So this notation theta t, as usual for convolution, for modifiers, is 1 over t to the n theta of y minus x over t. So what this does is it takes the function theta with support in the unit ball, and it shrinks down the support. So theta t has a support in the ball with radius t, and this 1 over t to the n here is to guarantee that the complete integral over theta t still is 1. Okay. And so what's about this function phi here? This function phi is nicely differentiable because the function theta is nicely differentiable, so it's C infinity. And this, as I already told you, this scaling here makes that the support of phi which is the support of theta t plus some y. So this is shifted by y. So it's the support of theta t plus y. And the support of theta t, as this is scaled here, is in the ball with radius t around the origin, and the shifted ball with t around the origin is just the shifted ball, is just the ball around y with radius t. Okay, so this is a function that is supported in this small ball, if t is small, and small t is what we're interested in. Okay, and t is less than the distance of omega j bar to omega j plus 1 complement. So y is in omega j, so this is contained in omega j plus 1. Because y has a distance of more than epsilon to the next omega j plus 1. T is less than epsilon j, so we are still in the next bigger set. Okay. Now, this in particular means that this function phi is a CC infinity function. So we can, and it has a support in omega, so it's a CC infinity of omega function. So we can apply our hypothesis, telling us that the integral over omega v of x theta t y minus x dx, this is 0. This is by hypothesis. Okay. Now, this has support in omega j plus 1. So this function somehow equals what Vj times this, and I can then integrate over whole of Rn. So this is Vj of x theta t of x y minus x dx. So this is the same because on the support of theta t, v and Vj is the same. And again, then we consider Vj as a function on Rn, but outside of the support, nothing. Out of omega, everything is 0, so we can write an integral over Rn. And what we now have there is a convolution. As I said, this was the aim to find a convolution. So now this is theta t convoluted with v j at the point y. And why is this good? Because we know what happens if you have a convolution with such a modifier thing. So this is an approximative unit. If you let t go to 0, then this will converge to Vj in LP, in every LP space. In every LP space different from L infinity. So what we know, this is in the first section of this chapter. So this is proposition 33c, which tells you that the limit t going to 0 of theta t convoluted with Vj, this is just Vj, and in L1. So if you restrict to omega j, on omega, then on omega j, Vj is just V. So the limit t going to 0 of theta t convoluted with Vj is just V in L1 of omega j. Okay. No, but what do we have? Now we have this equality here. So theta t convoluted with Vj is y at the point y is 0 for every y in omega j. And if you take t to 0, this goes to v. So take the limit up there and you get v's 0 almost everywhere on omega j. And now this finishes the proof, because the omega j exhausts all of omega, so this gives you that v is 0. Okay. So, what does this help? We now have, for every ck function, there is a unique function in L1 log satisfying this equality of partial integration. And now we turn things around and take this as a definition. So we say, if we have a function u, let's say in L2, and there is some function u alpha that satisfies this equation with u alpha at the place of d alpha u, then we say this is the weak derivative. Just by definition. So we take this partial integration formula as the definition. So this is definition 3.5. And this then is a way to define derivatives using integrals. And that's somehow why this fits better to the L2 setting. So we start with a function that is even in L1 log. We take some multi-index alpha and in the integers and 0. And then we say that the alpha derivative of u exists weakly. So this is now a definition of weak differentiability. If you have this formula of partial integration for some function u alpha, so if there exists a function u alpha, also in L1 locally integrable on omega, such that you have the equation up there, so integral over omega u times the alpha derivative of phi equals, okay, the bunch of minus signs that you get when you do the partial derivative, partial integration, times integral u alpha phi dx. And this must be valid for all phi in cc infinity of omega. So for all test functions, you have to have this partial integration formula. And if there is a function that satisfies this formula, then you just call this function the alpha derivative. And we will use the same symbols as before. So in this case, we will write d alpha u for this function u alpha. We just reuse the same symbols. This is okay because we have seen above, whenever you have a classically differentiable function, then it will be weakly differentiable. It satisfies the formula of partial integration, so it is weakly differentiable, and the weak derivative and the classical derivative are the same. So it's somehow okay to use the same symbol whenever the two notions of differentiability are the same, they coincide. But we will see in a moment that using this form of differentiability, there are more functions that you can differentiate than just the classically differentiable ones. So it's somehow an extension of this symbol. And it's also okay to say it's the weak derivative because we've seen, you take again the fundamental lemma of characters of variations. If there is such a function in the L1 log that satisfies this equation, it's a unique one. So if there is a weak derivative, it's unique. Okay, and some more notation. If it exists, we also take the notation of the gradient. So if all the weak derivatives of first order exist, you put them into a vector and we call this the weak gradient. Okay. Okay, and we've seen above, classical derivative implies weak derivative, otherwise the name would be awfully badly chosen. And the weak derivative, if it exists, is unique. And now the natural question is, did we really gain something? So are there functions that we cannot differentiate in the classical sense, but then that we can differentiate in the weak sense? And the answer is yes, there are many of them. I will show you a small example. Example 3.7. And this is what is the first example in a beginner's calculus course that are told it's not differentiable, it's the absolute value function. I will show the absolute value function is indeed weakly differentiable, even if it's not classically differentiable. So let's call this u. So consider the function u going from the reals to the positive reals or to complex numbers. Doesn't matter. I write to the complex number because we will work in complex Hilbert spaces in all this course. So clearly this goes to R plus. And I claim this function is weakly differentiable. So how do we see this? Take some test function, take some CC infinity function on R. We're on R. So n is 1, we're one-dimensional. And then try to find a function that satisfies this equation. So we write down integral over R u times phi prime. And we try to, this is the left-hand side, we try to get the derivative to the other side. So, okay, what is this? Now we can do a case distinction for the absolute value. So for x going from 0 to infinity, u of x is just x times phi prime of x dx. And from minus infinity to 0, it's minus x, so minus x times phi prime of x dx. And now it's just the usual integration by parts thing. So we do the partial integration, and this gives us, here we take the derivative over there, this gives us a minus sign. Then there are boundary values, but boundary values always vanish. What happens in 0? Yeah, you have to pay attention in 0. Yeah? So this is and in 0 x is 0. So if in infinity the boundary value for phi is 0, and in 0 x is 0. So you do not have boundary values here. So you get minus integral from 0 to infinity. Derivative of x is 1. Phi of x dx. And here you get the minus sign from the partial integration. So you get plus integral from minus infinity to 0. Derivative of x is again 1, and you have phi of x dx. Okay, so what is this? This is minus the integral 0 to infinity, minus infinity to infinity sine function of x dx. So minus sine from minus infinity to infinity, the sine function is a minus sign, and from 0 to infinity, the sine function is a plus sign. Okay, this works. Phi of x dx. Sine of x, phi of x dx. Okay, and this is exactly the formula that we needed. So this tells us that u is weakly differentiable and that the derivative is the sine function in the weak sense. Now you can ask, what is about the value of the derivative at 0? And I say this doesn't matter because the weak derivative is just a locally integrable function. So the value at one point is of no interest. In this sense, the weak derivatives does what one thinks from the first moment in the calculus course. The absolute value somehow is differentiable. There's only this one point in zero, and the derivative is -1 for negative arguments and +1 for positive arguments, and the value at 0 now is no longer of interest. So if this works so fine, let's try once more. So the question is the absolute value function perhaps twice weakly differentiable? And this example is here to show you the limits of this notion. So it's not. So the sine function is not weakly differentiable. And we will see this by contradiction. So suppose the sine function would be weakly differentiable. Then how should the derivative look like? So let's suppose it's weakly differentiable, and let's call its weak derivative w. What should this function w to do? Okay, we know by the definition of the weak derivative that whatever test function you take, it has to hold that w times phi, integral of w times phi, is the same as integral minus the integral of sine function times phi prime. This is the definition of a weak derivative. The integration by parts formula. Okay, so we can expand this using the sine function. So this is the integral from -infinity to infinity of phi prime, plus the integral, or minus the integral of 0 to infinity of phi prime. This is just putting in what sine is. So it's -1 on the negative, so cancelling this minus, it's +1 here. So this is a minus here. Okay, and now this is fundamental theorem of calculus. If you do integral over phi prime, you get phi at 0 minus phi at -infinity, but this is 0 because it's a CC infinity function. So this gives phi of 0. This gives 0 here and phi of 0 here. So this is phi of 0 minus phi of 0, so 2 phi of 0. Okay. And now take the fundamental theorem of calculus of variations on omega being R without 0. So the fundamental theorem of calculus of variation was just proven on an open subset of Rn. So take this open subset. Then what you find is on omega, if you have a CC infinity function on this set omega, then phi of 0 is 0, because 0 doesn't belong to the thing. So this is always 0. So what you find is that for all CC infinity function on this omega, this integral is 0. So the fundamental theorem of calculus tells you that w is 0 everywhere outside the origin. And not the fundamental theorem. The fundamental theorem of calculus of variation tells you that yields that w is 0 almost everywhere on R without 0. Okay, but the 0 point it's also null set, so w is 0 almost everywhere. Or so if you now take a test function on the whole line, that you can choose this test function in such a way that the value at 0 is 1. No problem. And then you get a contradiction, because then you get that 2 times phi of 0, which is 2, is the same as integral over R w times phi prime. But you know that w is 0, so this is the integral over 0. This is 0, and 2 isn't used to being 0. So this is a contradiction. Okay, so we learned that the weak derivative does generalize derivatives a little bit, but there are limits. So there are functions that, in this sense, are not differentiable. For instance, the sine function. Okay. Now the natural question is, how much of the things that we all have as in our mathematical genes about derivatives, so calculation rules for derivatives and all the stuff, remain valid if you work with weak derivatives. So let's do a little bit. Let's collect some things that remain true. And this is Lemma 3.9. And the good message is most of the things that you are used to just remain the same. So in particular, calculation rules for derivatives work fine. So we take k as the order of differentiation. We take a multi-index with length less or equal to k. We take some complex scalar lambda, and we take two locally integrable functions in omega such that all weak derivatives up to order k exist, or of order k, of order less or equal k exist, and then take some test function. Okay, this is all the stuff that I need to formulate all the calculation rules. And then, first thing, weak derivatives are still linear stuff. So if you have a linear combination of u and v are weakly differentiable, then you can use linearity. So this is the same as the weak derivative of u plus lambda times the weak derivative of v. So this is the first thing. Second thing, derivatives of derivatives are the corresponding derivatives. So if you take your function u and take some derivatives, so the first 5 derivatives, and then you do the next 3, it's the same as doing all 8 at the same time. This is intuitive, but one has to check, and it works. It's clear for the classical derivative because it's defined in a recursive way. So the nth classical derivative is the derivative of the n minus first. But here it's not that clear because you have the third derivative is just defined by existence of a function, so it's not immediately clear that the third derivative is the derivative of the second. But it works out. So if you take some multi-index beta that is less than alpha, and you first differentiate beta times, and then you add the rest, then this gives you the full derivative alpha. And last thing, product rule, or more general Leibniz rule, also this goes through. So, or at least it goes through if one of the products is nicely differentiable. So if you have the product eta u, eta CC infinity function, u weakly differentiable, and you take a derivative, then you get the usual Leibniz rule. So this is the sum over all multi-indices that are less than alpha, the multi-index binomial coefficient alpha over beta, d alpha minus beta u, d beta eta. So this is the Leibniz rule for weak derivatives, and you need with one of the two factors to be smooth. And you will see in the proof why. So I will give you the proofs of B and C. Showing that it is linear is really not exciting. This is just because all integrals here are linear, and you take this apart and it works. Okay, so what happens in B and in C? So what do we have to check? We have to take the beta derivative of u and do alpha minus beta more derivatives. So we take the beta derivative of u and we apply to the alpha minus beta derivative of phi. Take again any test function in omega. And do the right number of minus signs in front. And now the important point to note is that whenever phi is a test function, all its derivatives have the same quality. So this is again a test function. So you can now apply the definition of the beta derivative and get this to the other side. So this gives you minus 1 alpha minus beta modulus plus the modulus of beta, integral over omega u, and then alpha minus beta plus beta, so d alpha phi. And this is the same as the length of alpha. Okay, and this shows you that indeed the alpha minus beta derivative of d beta u is defined, and yeah, here it has to be d alpha. I have to take it to the other side. So d alpha u. So now, so the alpha derivative of u is defined, and it's the alpha minus beta derivative of the beta derivative of u. Okay. So, and then the Leibniz rule. I will not show the full Leibniz rule because this is an awful induction over the ordered derivative. So I will show you I will show you one derivative. So I will show you a product rule. And once you have a product rule, finding the Leibniz rule from product rule, this is just doing induction. So let's see that the product rule works. So we only consider the case where the length of the Milde index is 1. And we take some partial derivative, and we want to differentiate eta u in the weak sense. So we multiply with the corresponding derivative of phi. That's what you have to do. If you want to differentiate a function weakly, you multiply with the corresponding derivative of the test function, you integrate, and you try to get the derivatives to the other side to have a phi on its own. Phi on its own. Okay, let's do this here. So this is integral over u. And now the point is that this eta is not just any local integral function, but a test function, so it's CC infinity. So let's put it over there, here. And then you find that this function here is a test function. Yeah, because products of test functions are test functions. So, no, this is too early. So what we now do, we try to get this as a derivative of eta times phi. So we do a product rule backwards. So this is integral of omega u, and then the derivative of eta times phi, and now correcting the error, minus derivative of eta times phi. Okay. Now you can do you can do a partial derivative, partial integration here. In the first integral, you have u times the derivative of eta phi. Eta phi is a test function. Now is the point. This is a test function. U is weakly differentiable by hypothesis, so you can take this over to the other side by taking a minus sign. So minus omega dju multiplied with eta phi minus integral over omega u dj eta phi. So, and what did we achieve? So perhaps to make it even clearer, this is integral over omega minus integral over omega eta dju plus u dj eta times phi. And this is weak derivative. Yeah, you have your function eta u that you want to find the weak derivative times the corresponding derivative of phi. And now you have rewritten this with a minus sign, or we have rewritten this with a minus sign and the phi on its own. So this is the weak derivative. And this is exactly what was claimed. The weak derivative of eta u is eta dju plus u dj. Okay, and then for higher order, for the whole Leibniz rule, just do an deduction. Okay, so this is the good news. Calculating rules for derivatives stay the same. Perhaps there is one question already in your mind. What is about nice theorems like if the gradient of a function, weak gradient exists and is zero, is the function constant? And the answer is yes, and this we will do after the break. So let's start again. And I already announced what the next proposition will look like. So this is proposition 310 that also gives us the result that we know from classical derivatives for weak derivatives. So if you have a connected set omega, and you know that your function is weakly differentiable with a gradient that is zero, so it's a locally integral function, weakly differentiable, then the gradient of u is zero if and only if u is constant. Again, going from here to here is not that interesting, so constant functions are classically differentiable, so they are weakly differentiable, and the gradient is zero. So the interesting thing is going from left to right. And for this, to prove this, we have to do some smoothing again by convolutions, and so we need somehow that the derivative, you know that if you have a convolution and you have the derivative of the convolution, somehow you are free to put the derivative on either of the two factors. And this is known, but what happens if one of the factors is weakly differentiable? Can we then also put the derivative on this factor? And the answer is yes, if you are cautious. So you have to do a little bit, or we will do a little bit, have some security things about the domain, or about supports. So the lemma that we need is, if you have a locally integrable function and you have a test function on all of Rn, again with the support of theta in the unit ball, and you then take again the truncated domains. So for epsilon greater 0, now set omega epsilon. So unboundedness doesn't matter now, but just as the set of all x and epsilon whose distance to the boundary of omega is greater than epsilon. And then what we have is, if u is weakly differentiable in omega, so for some multi-index alpha, and you take a t that is less than epsilon, then at least in some omega 2 epsilon you can do what you want. So then the alpha derivative of theta t convoluted with the characteristic function of omega epsilon times u Why do I have this characteristic function? Again, the u is only defined in omega. For convolution, you need the whole space. So that's why we cut away the boundary of omega. And again, this has to be understood as a function on the whole space, but just taking it 0 outside of omega epsilon. So these two functions can be convoluted. And then, you can put the d alpha here. This is no surprise because theta t is smooth, but the nice thing is you can put it here and you can even put it here. So then this is theta t convoluted with the characteristic function of omega epsilon times the weak derivative of u. And it's also the same as the derivative of theta t convoluted with the characteristic function times u. But the most important part is this one. And this is true in omega 2 epsilon. So you have to stay away from the boundary. Okay, and this I will not prove this one, so the proof is in the lecture notes. It's technical stuff, convoluting things and smoothing things out, but it works out. But we will use this formula to prove that if the gradient is 0, the function is constant. So now the proof of 310. And again, this part is the easy part. So we go from left to right. So we have a weakly differentiable function with a 0 gradient, and we try to prove that it's constant. And the way to do it is just to start small, just to take a ball. So take some x in omega, take a ball in omega, and take the radius so small that you have some space left so that the ball around x with the 3 times the radius is still in omega. Okay, and this ball I will call B for the next calculation. And we will just, for the moment, only look at balls of this sort. So balls in omega that, if you triple the radius, still stay in omega. Okay, and then choose again some nice test function to create a modifier. So take some continuously arbitrarily often differentiable function with compact support, such that, again, the support of theta is contained in the unit ball, and the overall integral over Rn of theta is 1. And now again, if you have such a function, you can construct theta t by doing the right scaling, and this gives you a modifier to make things converge in the right sense. So now we know that u is in L1 log. So in particular, u is in L1 of the ball around x with radius 3r. Because if you close it up, this is something compact, and on compact sets this is different integral. And now you can use our lemma 311 here, at least for t less than r. No? So this means if t is less than r, then we know that we are inside omega epsilon, and everything is okay. And then you get that the jth derivative of theta t convoluted with, now we multiply u with a cutoff function on the ball x with radius 2r. This is also still in omega, this is okay, but this gives us a security distance of r to the ball with radius 3r. So the support of this function is in every direction. Is the support of this function as a distance to the complement of omega of at least r, because the ball with radius 3r is still in omega. So t is less than this distance, so we are in this setting. Okay, so we can take this derivative in here by 311. So this is theta t convoluted with the cutoff function times the corresponding derivative of u. Okay, but we know that this is 0. This is now hypothesis. U has a 0 gradient, so this is 0. Convoluting something with 0 is 0, so this is 0. And this is true for every j going from 1 to n, because the whole gradient is 0. And now one looks at this and thinks, what does this help? And the upshot is, this is a smooth function. So if you have a convolution, the result is, well, this is a convolution with the L1 function. This is L1. You have a convolution with smooth with L1, so this is smooth. So this derivative is a classical derivative, or you can interpret it as a classical derivative, because this is a smooth function. So what you have here, you have a smooth function and all the derivatives are 0. But then we know what to do. So this function is constant. So somehow we with this trick, we get again back to the known result about classical derivatives. So what we now know is that the function theta t convoluted with the cutoff version of u, that this is constant. At least, let's say, in all the ball B. Now, what you know is, now let t go to 0. For every t, it's a constant function, and you know that it converges, because theta t is a modifier, this converges to the cutoff version of u in L1 of Rn. Now, if you have constant functions then converge to something, okay, so first thing, you have a convergence in L1, so take almost everywhere convergent subsequence. So then you have a sequence of constant functions that converge to something, so there's not much choice for the limit. Constant functions can only converge to constant functions. So what you know is that this function is constant. So what you get is, or at least on a little bit smaller bore, what you get is that u is constant in B. So let's make sure that we keep in mind that all this reasoning was just on one ball. So what you now know is, whenever you take a ball that is in omega such that if you increase its size by the factor of 3, so you still remain in omega, then you are constant. But in practice, this constant could be different on every ball. For every x. Once you change the x, the constant could change. This seems weird, but the proof doesn't tell you that that cannot happen. So we now have to make sure this cannot happen. Okay, so what we do is we take any of the balls above, so fix any ball B0 as above, and okay, set C to be the constant that belongs to this ball, just to fix notation. So we take one of these constants. And then we do what hypothesis didn't we use up to now? We used it once, but we'll use it again. We used that omega is connected. Now we already used it when we talked about the classical derivatives. Also for classical derivatives, you only get constant. No, because there we were on the ball. The ball is connected. Okay, so up to now we have not used connectedness, so we'll use it now, and we will do an open-closed argument. So we will show that the points x and omega where there is a ball with exactly this constant is open and closed. And once you have that, it's by connectedness is all. So we define the set M to be the set of all x and omega such that there exists a radius positive such that u is exactly this constant on the ball around x with radius r. Okay, and what we want to show is that M is all of omega, because then we are done. Then we know that for every x and omega, there is a ball around x, where u is exactly this constant c. So in particular in x it's c, so it's c in every point. Okay, and to do this we have to prove that this M is non-empty. Okay, that this M is non-empty is clear because we chose this constant c to come from one of the B zeros, so there is at least one ball somewhere out there where this works. So it's non-empty. We have to make sure that it's open and closed. So it's open because these balls are open. So once you have an X where there is a ball around where the function is exactly this constant on the whole ball, if you are close enough, if you take a point that is less than r away from X, you still find a ball where this holds. So this is an open set. The important point is to show that M is closed. And to do this, take some sequence xj contained in M that converges in omega, so that x0 is the limit. It's a convergent sequence, and the limit is in omega, and what we have to make sure is that x0 also belongs to M. And now the point is, wherever this x0 is, it's somewhere in omega. And omega is an open set. So if you do a really small radius, you will find a radius positive such that the ball around x0 with radius r is such that it qualifies here. Because x0 has a positive distance to the boundary. Take the distance divided by 6 and you will find a suitable r. So there is a ball around this x0 on which the function is constant. The only point is it could be a different constant. But what we know is that u is equal to some constant, let's say constant prime, on some ball around x0 with radius r. But now the nice thing is that this sequence xj converges to x0. So at some point, our sequence must get into this ball. So for j large, we know that xj is in this ball x0 with radius r for j large. Okay, but these xj are in M. So around these xj, there is a ball where the constant is okay. Okay, now around xj, there is a ball where the constant is c prime, and there's a ball where the constant is c. So it's c is c prime. So c is c prime, and this. Now we have a non-empty Clopen subset of omega. Omega is connected, so M is all of omega, and this tells us that U is constant. So you see, you have to do some work, but the nice result is this method to show that the function is constant also works for weak derivatives. One more really good news about weak derivatives. In one dimension you can even get a fundamental theorem of calculus. And this is a really nice thing. So this is the fundamental theorem of calculus for weak derivatives. And it more or less looks the way you are used to it. So we are in one dimension, so let's take a bounded interval. And okay, what you need that your function and the weak derivative are L1 functions. So this is the condition that you have to make. We're not in L1 log now, but we are in L1. So if you have an L1 function, then the following are equivalent. The first thing is U is weakly differentiable with an L1 derivative. So U is weakly differentiable in AB, and the derivative is again an integrable function. And secondly, there exists some function f in L1, and there exists some constant. So this function f, this will be the primitive. This will be the antiderivative of u. So there exists a primitive and there exists some constant such that you can write u of x as this constant plus the integral from a to x f of s ds. Almost everywhere for x in AB. So what this tells you is whenever you have a integrable function that has an integrable weak derivative, then you can write down the formula that you know from the fundamental theorem. You can write u as a constant plus integral over the derivative, and we will see that in this case, of this theorem, in this case, f equals u prime. In this case, u prime and f are the same. And then it's really what you are accustomed to as fundamental theorem of calculus. U is some constant, so u of a usually, plus a to x, u prime of s ds. But it's good to formulate with a constant, because u of a, u is L1, so this is not defined, is only defined in an almost everywhere sense. So writing down u of a is a little bit tricky. We will come to that, back to that in some minutes, but it's a tricky thing. You cannot write down u of a and at the moment and hope that this gives sense. So in this case, u prime is f, and this function over here, so c plus this integral, what we've found now, so if we have a weakly differentiable function as integral with integrable derivative, we can write down u as a constant plus the integral over the derivative. And this function here is continuous in x. This is a integral of an integrable function, so this is a continuous thing. This is continuous in x. Now, okay, what does that mean? That means if you have a weakly differentiable function in L1 and the derivative is also in L1, then u has a continuous representative. And this comes somehow completely out of nowhere. So u is only integrable, but if you know that the derivative is also integrable, then u has a continuous representative. So this function here is a continuous, and I write it's the unique continuous representative of u. So this fundamental theorem of calculus tells you two things, many things. It tells you the formula is the same as you are used to, and it tells you whenever you have in one dimension, and this is really one dimensional, whenever you have a function that is integrable with an integrable weak derivative on an interval, then this function is more or less continuous. So it has a continuous representative. And this is also the reason, if you think back, we saw that the absolute value function is weakly differentiable and the derivative is a sine function. And then we tried to do a weak derivative of the sine function, and this failed, and now you see it had to fail. Because the sine function has no continuous representative. And the fundamental theorem of calculus tells you it has, if it's weakly differentiable on an interval, and the function is L1, at least this says there cannot be a L1 weak derivative of the sine function. Okay. So let's prove this really important result. And it's also an equivalence, so we have to show we have to go from A to B and from B to A. So let's go from A to B. So we define v of t v of x, to be the integral a of x u prime of s ds. If you go from a to b, this is well defined, because u is weakly differentiable and the derivative is one, so we can write down this v. And we will see, and then, I have to do the other direction first. Okay, so let's go from b to a. We will finish this in some minutes. So we show that if there is such an f that you can write u in this way, then u is weakly differentiable, and the f is u prime. And to do this, we take v as this function on the right hand side. So set v of x c plus integral from a to x f of s ds. F of y dy. And this as a function in x going from a to b. Okay, then we know, because f is integrable, that v is continuous, and it is continuous up to the boundary. It's continuous on the closed interval ab. And this is just by dominated convergence. So if you take this v and you do some limits, x going to something, the f is L1, so you have a measurand for the integral, and by dominated convergence you will get that if you do x to x0, v of x tends to v of x0. Okay. And you get, now we have to look at the derivative, so let's take any test function. And then we get that the integral of from a to b v of x phi prime of x dx, this is what we have to look at. We want to show that v is weakly differentiable. No, we have to want to show, this has to be, I want to show that v is weakly differentiable. And then that v prime is f. That is what we want to show. We have as a hypothesis that u is given like that, so we take this u, and we show it's weakly differentiable with the derivative f. Okay, so we look at the v, multiply with the derivative of phi, and now we have to get the derivative to the other side. So we put in the definition of v, so this is integral of c times a to b phi prime of x dx, so this is just the c part of v, which is the easy part, plus, and then, okay, what do we have? We have integral a to b. Now the v is again an integral a to x f of y dy, and phi prime of x dx. Okay. Now the first integral is an easy part. What do we have here? You have an integral over phi prime. So this gives phi at b minus phi at a. But phi is cc infinity of the interval ab, so phi of b and phi of a is 0. So this integral just is 0. So what we are left with is this one. And what we do here is a Fubini, so we change these two integrals, which is okay because everything is a 1. So what we get is integral from a to b, integral from y to b. Now let's take the f out. F of y, integral from y to b, phi prime of x dx dy. And now you see why I wanted to do a Fubini argument, because now in the middle I again get an integral over phi prime. So here I can just take the fundamental theorem of calculus from calculus course. So this gives you phi of b, which is 0, minus phi of y. Okay, phi of y could be something. So this is minus integral a to b f of y phi of y dy. And this is exactly what we want. You get integral a to b v times phi prime is minus integral f times phi. This means v is weakly differentiable and the derivative is f. So we are at a. And now we can finish our proof going from a to b. So we have to prove that if u is weakly differentiable, we find such a function f that we can write u in this way. What is the natural candidate for f is u prime. So what we try is to define v like that and to show that v and u will only differ by a constant. But somehow, or then as on the right side, as we just did, you do this calculation here. So this calculation is the only difference here is that we had this constant c here, but this was the 0 anyway. So you do the same calculation here again. So this gives you that v prime, that v is weakly differentiable and the derivative is u prime. So somehow we used b to a here. And now, okay, this means v minus u prime is 0. And now we can take our result from 20 minutes ago that if you have a weakly differentiable function whose derivative is 0 on a connected set, we are on an interval, then this function is constant. So this tells you there's a constant such that u minus v is constant, and this means that u is given by c plus v, and this is what is to be shown to have b. Okay, this is the fundamental theorem of calculus. And so you see these functions that are integrable with the integrable weak derivatives. They are really nice functions. In particular, they turn out to be continuous, and these functions usually are called absolutely continuous. So if you find this word somewhere, absolutely continuous just means that. Or there are several definitions. What one way to see it is absolutely continuous functions are functions on an interval that are integrable with the integrable weak derivatives. Okay. Now one more corollary. I already stressed this, but let's put it on the blackboard because it's important. So if you have a bounded interval in the reals and you have an L1 function with a weak derivative that is also integrable on AB. So if you have an absolutely continuous function, then U has a unique continuous representative. So there is a representative U tilde, which is a continuous function on the closed interval AB. And you even get a norm estimate. So if you take the norm of this representative on the continuous function, so the supremum norm. So if you take the supremum norm of this U tilde, I claim this is less than 1 over the length of the interval times the L1 norm of U plus the L1 norm of U prime. So you even control the supremum of this continuous derivative, if this continuous representative, if you know the L1 norm of U and of U prime. So proof is not long, because we have the fundamental theorem of calculus. So So the existence of this U tilde is just the fundamental theorem of calculus, and the fundamental theorem of calculus does not only tell you there is some primitive, but the nice thing, it gives you a formula for the primitive, and the formula is a good starting point to do an estimate. So for all x and y in AB, we get that U tilde of x in modulus is U tilde of y plus integral from y to x U prime of s ds. You could say, why does he know that the constant is this value? Yeah, because we know that the constant is just this difference between the value of the function and this integral. And this is okay. So we can write down the usual thing, and now we can write it down. I told you to be cautious. In the theorem up there, there is the constant c, and at the first glance, it's to write down an u of a instead of the constant c is a bad idea because u of a is not defined. Yeah? It's an equivalence class of functions. But now we know that there is a continuous representative, and for a continuous representative, this is completely okay to write down. Yeah? That's why here you have u tilde. This is the magic about this theorem that tells you that functions that these functions have a continuous representative. You can write down like that. Okay, once you have that, we can do some little estimates. So you do a triangle inequality. This is less than the absolute value of u tilde in y plus absolute value of this integral. Take the integral inside, the absolute value inside, making things greater, integrate from a to b, and what you get here is the L1 norm of u prime. Okay, now we get for every x and y, you have that the value of u tilde of x is less than u tilde of y plus this norm. This is not exactly what we have here. Okay, this term is okay. Well, we have to do a supremum over x, but what happens here? And now the idea is to just average this inequality over the whole interval. So we know that the absolute value of u tilde of x can be artificially written as 1 over b minus a times integral from a to b u tilde of x dy. This is doing nothing in a fancy manner. I take this value and I take this constant value in y and do a mean value integral. But the good thing is now you can put this estimate in there. So this gives you 1 over b minus a times the integral from a to b u tilde of y dy plus the average over this constant, but averages of constants are the same constant. Yeah, so this is again u prime L1 AB. And now you find exactly what you want to have here. 1 over b minus a. This is the L1 norm of u. Oh, so this gives you the claim. 1 over b minus a. L1 norm of u plus L1 norm of u prime. Okay. Yeah, now the right hand side does no longer depend on x, so just take the supremum over x and then you have this. Okay, so this is what we have to know about weak derivatives. There are a nice class of functions, the weakly differentiable functions, and I hope I convinced you there are many nice theorems that we know from classical derivatives that remain valid. And so it's a good concept. And in the beginning, I promised you that this will reconcile the derivatives with the L2 viewpoint. There was no L2 up to now, so now we will do this. We will now, up to now it was more in the L1 world, and now we will go to L2. And we will look at L2 functions whose weak derivatives are again in L2. This is okay. We defined weak derivatives for locally integrable functions. Every L2 function is locally integrable because on compact sets L2 embeds into L1. So if you have an L2 function, you can ask whether it's weakly differentiable. This is a sensible question. And we will look at L2 functions whose weak derivatives are again L2 functions. And this leads to the notion of a Sobolev space. So this is section 3 of this lecture, of this chapter. So we talk about Sobolev spaces. And they are usually called H. So Hk of omega is the kth order Sobolev space. And so here's the exact definition. Take some integer k in the naturals, and then I will define, and omega is still an open subset of Rn, and the space Hk of omega is now, it's somehow the set Ck is the set of our continuous function whose derivatives up to order k are also continuous. And we mimic this now. We take the set of all L2 functions whose weak derivatives up to order k are all L2. And this gives Hk. So this is the set of all L2 functions, or the vector space of all L2 functions, such that the alpha u is also an L2 function for all multi-indices alpha of length less or equal k. So this means it's the set of all L2 functions such that the weak derivatives up to order k all exist, and all of these derivatives are L2 functions. So this is called Sobolev space of order k. And what we've already... No. And now I already wrote Sobolev space, so one has to check that this is really a vector space, but that is not complicated. So L2 is a vector space, and we know that differentiating, if it exists, is a linear thing. So whenever you have two functions in this space and you do a linear combination, you stay in this space. But the question is, how nice is it in addition? Is there a useful norm on this space? Is there a scalar product? Is it complete? All this functional analytic stuff. And the good news is it's a really, really nice thing. This is Theorem 316. And it says this space always is a Hilbert space. And it's even a separable Hilbert space. So somehow it's as nice as L2. Now I write down Hilbert space. What is the scalar product? And the scalar product can be, somehow one can guess it. You just take it from L2. So you have two functions, uv, and you want to do a scalar product, and you know that there are many derivatives, and they are all L2. So what you do is you just sum up all the relevant L2 scalar product. So you take any multi-indices that are less or equal k in length, and then you take all the weak derivatives, d alpha u and d alpha v, and you do the corresponding L2 scalar products, and you all sum them up. And then it's not too difficult to see that this is again a scalar product. You do linearity, just take everything. The L2 scalar products are linear, the sum is linear, and take them apart and put them again together. This works. It's symmetric. It's anti-symmetric, all the stuff that you need. You could think a little bit about definiteness, but if you take what is the corresponding norm, so the corresponding norm just turns out to be you put in uu and the square root, so this gives you, take the sum over all multi-indices of length up to k, take the square of the L2 norm of the alpha derivative, sum them all up, and then take the square root. This is the norm. So what happens if this norm is 0? Okay, this means that the sum inside the square root is 0, But if the sum of positive numbers is 0, then every summand is 0. So in particular, the summand for the 0 multi-index is 0. So you get that the L2 norm of u is 0, and this means that u is 0. So this is a definite thing. And so this is a nice Hilbert, this is a nice pre-Hilbert space. So you have a scalar product, and the only thing to prove left to prove now it's not only a pre-Hilbert space, a Hilbert space. So it's complete with the scalar product and it's separable. And this proof will then be the starting point for the next lecture. Thanks today for your attention and have a nice day.